Welcome to another Coding Like Mad Matlab tutorial. Today we're doing part 2 of our Neural Nets in Matlab series. If you missed part 1, which was about making regression networks, you can click the link right here. In today's video, we're going to talk about how do you classify input data using a neural network. We're going to use an example where we classify colors. So for example, here you can see some labeled red, green, and blue data for the color gray. And then what happens if we run that through a neural network in order to classify what color it actually is. You can see the data is pretty messy to begin with, but at the end, the neural net knows exactly what the color gray looks like. If you like this type of video, don't forget to subscribe to our channel and comment below if you have suggestions for what you'd like to see next. Okay, so to get started, we're going to look at some example data. So the idea with the classification problem is basically we need to have an input space and an output space. So for all my examples here, I'm going to be looking at some color data from Randall Munroe that has the red, green, and blue values and then what someone would actually call those. So what we want to do is train a computer to understand what the color green actually looks like in terms of red, green, blue space, or the color blue, or the color purple, right? So I have provided a dataset on the GitHub called shortcolordataset.csv so you can follow along at home. What's in this dataset? Let's just take a quick little look-see. So I'm going to read a data table, and if I do this and wait a couple seconds, I get about 170,000 lines, I think. Yeah, it's 176,000 lines. And as you can see, I took the unique values in the table.color color name, and we have things like magenta, orange, pink, purple, red, sky blue, tan, teal, and so forth. I think it's worthwhile to actually look at what these different data sets look like. So if we visualize the red, green, blue color space like I did during the opening sequence, you can see that, for example, the blue color is indeed mostly blue data points, but there's a bunch of other junk here. And I think this is important. There are different approaches to machine learning. We're trying to teach a mapping between this red, green, blue space and some labels, but there can be real disagreements between people on what is a color blue. Like, when does blue become sky blue? Or for that matter, the person interpreting the survey, did they think sky blue was a real option, or did they think only blue was an option? The other thing you can see is there are a bunch of data points in this blue plot which clearly aren't blue. So I would say there is a, let's call it a jerk factor on the internet, people who fill in just terrible things. So the point I want to make is, in this data set, there is no right and wrong answer known. We just know what people call those colors, and I want to teach a machine that. So how do I do that? What we want to do now is to make our data usable for training a neural net. And I'm going to do this in two different parts. So for ease of use, I'm going to, first of all, we're going to convert our input space into just a vector. I mean, that's very straightforward. We're just taking the red, green, and blue features and putting them side by side. But what we're doing for the output space, the target, is much more interesting. I'm using a command into vec here, and I'm feeding into it the specific values which were used or output by the find group command. So if I take a look at the values in G, let's say I look at the first 10 values, and you can see that we have a set of integers. So integer 2 was blue, it turns out. In fact, we can even look at ID value 2. You can see that's blue. ID value 10 was light blue. So the colors as labeled by the person doing the survey here were labeled blue, blue, light blue, and then whatever color number 7 was. However, for the neural net, we want to actually convert this into what's called a one-hot encoding. So if I take a look at target, and I'm going to do, just take a quick little look-see at the size of target, good. So if I do the first row of target, so this is supposed to encode the color blue. But what you see is it's a weird notation. It says there's a 1 at the position 2, 1. Well, it's actually because this is a sparse matrix, and I can convert it to a full matrix by using the full command. And what you see is that its actual values are 0, 1, and then a long series of zeros. This format is called a one-hot encoding, and the idea is that instead of telling the neural net that it needs to learn that a color blue is a value 2, instead a color blue corresponds to a vector with unit direction in the second dimension. So we've gone from a one-dimensional space with 24 possible values to a 24-dimensional space where each dimension can only be 0 or 1. This is a really standard approach for dealing with categorical variables in machine learning. Doesn't matter where you are, so you'll see this all the time. And we need this because although I could make a neural net predict this otherwise, it starts to suddenly matter a lot what order the colors are in, which is weird. It shouldn't really matter what order they're in, and how do you order a color anyway? Okay, so now that we've got our input and output space set up, we need to actually go ahead and train our network. So we do that actually very simply with a piece of code that looks like this. If you remember the regression tutorial that I previously did, we had a very similar format. So the first thing we have to do is actually create the network. And I do this with the pattern.net command. In the regression case, this was a feed-forward network, but the argument's the same actually. That 10 says that I want to have one layer with 10 hidden nodes, and I can check this using the view command. As you can see here, there's one hidden layer with 10 nodes in it. But you see that the output and the input both have dimension 0. What's up with that? Well, I haven't actually run the train command yet. So in Matlab, the input and output space is not actually populated until you actually run the training through it. So we can do that by using the train command. We just tell the train command which network to use, the input space and the output space. So very straightforward. Let's go ahead and do that. And what you can see is that now looking at the top of the screen, the input space is now 3-dimensional and the output space is 24-dimensional. So it outputs 24 numbers, and those 24 numbers are the probabilities that it is going to be in any individual category. So if the first, or if say the second dimension is very high, that'll be an indication that you're most likely in the blue case. We saw the 7th dimension was light blue. So if your 7th dimension is high, maybe you're more likely to be light blue. And if they're both high, maybe it can't tell the difference between them. You can see there's a lot of information available on this screen. In the second section where it's the algorithms, you can see that it's using a scaled conjugate gradient training algorithm, that it's using a random data division, and maybe most importantly that it's using cross-entropy. So I'm going to talk about cross-entropy in some detail in the video. So here's a little bit of math on screen, and what you can see is that the mean squared error approach taken by the regression networks previously tries to minimize your square error, which makes a lot of sense for a single continuous output. However, for a categorical system like this where we're trying to classify, what we really want to do is not minimize our squared error to a label, because what does it mean to be 0.5 away from being blue? That doesn't make any sense. What we want to do is penalize the network from making guesses it's confident about when it's wrong. So that's what the cross-entropy function shown here actually does. When the probability of a particular class is high, that makes the penalty for making a mistake there high. When the probability is low, we don't penalize it as heavily. Cross-entropy sounds like a scary name, but it's basically just we're going to weight by the confidence the network has. And the result is that it tries to make high confidence guesses where it has good information and low confidence guesses where it doesn't. And that's really nice because we have the ability then to look at this and give the network the chance to say, I don't know what the right answer is. And for machine learning, that's really useful. Like, you know, if you have a self-driving car, boy, I'd like it to say, I don't know what to do, and go to a default option like hitting the brakes, you know? Like, there are times when it's good to say, I don't know. Okay, so let's go back to our network, which is now finished training, and you can see it took 209 iterations to finish and 1 minute and 42 seconds with a particular performance score, and at the end you can see it had some validation checks that it did. So let's click the performance icon here at the bottom, and what you can see is that over time this cross-entropy metric improved. If you want, you can actually watch this live while it's training. It's pretty mesmerizing. I do it quite a bit. And if you're using this data set, it shouldn't take that long to run. In fact, we can more or less rerun it now. So let's do that. So if I click performance, we can watch it evolve over time. And this isn't actually the most interesting part of this. So of course that's going to improve. Let's pop up training state. Training state here shows the gradient the network is following. So you expect that you might think this is always going to go down, and I think for this network it more or less will, but actually for more complicated problems you'll see this jump around, because the gradient is one of the knobs that the optimizer will use to make things converge better or worse. More interesting is this val fail. So the way that neural networks are trained in Matlab, and you'll see the same trick used in TensorFlow pretty frequently, is it will use a validation data set. And this validation data set is basically a second data set that it checks that is never used for training. And what it will do is continue to train until this validation data set actually gives a worse answer when you perform a training loop. And the idea is this is data it hasn't seen before, so if the network is generalizing well, the validation data set should continue to improve over time. And if we start to see that not happening, it's a sign that overtraining is occurring. We can also generate, for example, the receiver operator characteristic curve. So this is the ROC curve. And this is a standard tool used in data science. So here I have an ROC curve for a classifier. So all it's trying to do is tell the difference between two different data sets. And as you can see, the true positive rate is plotted on the y-axis and the false positive rate on the x-axis. And the idea is that depending on where we set a threshold for our classifier, we will have a higher true positive rate. That is, we're going to flag more often, but as we flag more often, the false positive rate increases because we're making more mistakes. So ideally, if we set a very low threshold, we'll barely ever flag. But on the other hand, while we won't make many mistakes, we won't make many correct guesses. On the other hand, if we set a very high threshold, we may flag constantly, but we'll be making mistakes all the time. So we'll get everything, but we'll also make tons of mistakes. So the ROC curve is a really nice way to check how we're doing it. What you want to see is a curve like this one, where we are very close to the top left corner. The area underneath this curve between the 1, 1 line that you see diagonally and this top corner actually is called the area under the curve, and is a measure of how good is our ability to differentiate between the classes we're interested in. So here we have 24 classes, and you can see that actually only this purple one is being struggled with at all, and it's the largest class. Okay, so next let's talk about how you deal with the outputs here. So if I run the neural network, I can do it basically just like a function. So here I'm going to plug in all of the training data I had and output a set of predictions labeled y. So here we're just using it like it's a function. The network is just a black box I can put in my vectors in, and it will go ahead and classify them. So what does this actually look like? Well, remember I said we're predicting 24 outputs. Here you can see I again predicted 24 outputs. Conveniently though, there is a command which inverts vec to int and will actually classify everything more or less automatically for us. So if I run that command, there we go, classes 1 to 10, and you can see what it actually classified them as. So If you remember our labels before, if I plug this into class, there we go. Here, let's just do the first three. So the first three were blue, purple, and cyan is what the outputs were, and the inputs for those, what those real labels were blue, blue, and light blue. So here it got the first one exactly right, blue and blue, whereas purple was classified as blue and cyan as light blue. Now cyan and light blue are almost identical. Purple, you can make some arguments over where the line is between purple and blue, to be honest. Looking at the data, I don't particularly trust that the internet labeled things in the most accurate way. So for me, this seems like a very reasonable result. And I will show the output from the models here. As you can see, if we visualize the outputs of the model for the color blue, there's a little bit of purple and a little bit of light blue. So let's actually compare the blue 3D render to the cyan render. And you can see the cyan color is actually on the border of the blue color. So this explains why it would have trouble distinguishing between blue and cyan. They touch. The same thing actually happens with purple, and this is weird. I didn't expect this, but there is a little sliver of purple in blue, and I think that this is inherent to the English language words. So finally, one of the things that I skipped when I did this before was the confusion matrix. So when you're doing the training, you can pop this up, but honestly with 24 classes, it gets pretty bad. So here I just wrote some code to calculate it anyway, and the idea is basically I'm going to look at what the output class was and what the input class was, and we're just going to count how often it got each class mixed up. So let's take a quick look at that, and as you can see, here's a display of that label. And you can see right away, first of all, this data set's imbalanced. There is way more blue, brown, green, pink, purple, and red than any other color. So people are way more likely to call something red, for example, than they are pink. And they're way more likely to call it green instead of dark green or light green. Like light green and dark green are both relatively rare in this data set. In fact, you could argue that according to the people surveyed on the internet, blue, brown, green, pink, purple, and red are really the only colors, and maybe magenta. So this confusion matrix essentially shows how often things are getting mixed up. So you can, for example, see light purple and light green were never classified correctly. Light purple and light green were always shifted. So for example, light purple usually got classed as purple, whereas light green usually got classed as green. And probably the reason for this is just there's so much extra green there that the things that we would call light green, you would say, well, okay, they're also green. So there's sort of overlap between the spaces. A confusion matrix here lets you work out where the neural network, or any classifier for that matter, is getting confused, like which things are not distinguishable. And if you wanted, you could try and push it to get the ideal situation, which is a diagonal line here. But the truth is in this case, I don't think there's a right answer. I don't think that it's worth pushing a neural network to try and produce diagonal here, because actually I think there's a fundamental ambiguity between the colors green and light green and dark green, and I don't feel that it makes sense to push it. Likewise, there will also always be confusion because people on the internet are bad people. No offense to those of you watching my video, I mean the other people. And so because of that, there are always going to be some junk answers in here where people have filled in the wrong answer. And there can also be completely well-meaning differences of opinion in what the color is, as well as differences of opinion due to monitor variation, and there may even be some people who are colorblind who also filled the survey in. In all of these cases, I think there's sort of good reasons not to try and force the neural net to capture things. What is cool here is that we can see the real color space. So I'm going to close on that. Here is a animation showing exactly what each of these colors is. And I hope you enjoy watching both this video and this animation, because I think it's really cool to see what these colors really are. Anyway, guys, have a good day, and I hope you will subscribe to this video if you enjoyed it.